Welcome to El Zoominario. Today, we're very excited to host Pablo Moreno-Yaeger. Pablo is a Chilean PhD student at the Department of Geoscience at UW-Madison. He has a master's in geoscience from UW-Madison and a bachelor's degree in geology from Universidad de Chile. He's currently investigating how volcanoes interact with glaciation, oh, I don't know how to pronounce that. To do that, he's working on Chilean volcanoes that were covered by 1 kilometer thick ice sheet around 18,000 years ago. Thank you very much, Pablo. We're very excited to have you here at El Zoominario.
Thank you, Claudia. Thank you for the invitation. Yeah, so today I'm going to talk about what are the hypotheses that indicate that volcanoes could be, the eruptions of the volcanoes could be related with glaciation. And we refer to glaciation as major events where there's a very thick and big ice. So this is the Arica volcano located in Chile. It's the most active volcano in Chile and among the most active volcano in Latin America. And you can see that on this side, it has a glacier. Now, during glaciation around 18,000 years ago, this ice was much thicker and thinner at the point that it was actually covering much of southern Chile and austral Chile. So as a background, as an introduction to show you what we do, briefly introduction what we do on volcanoes. Basically, I will try to share this here. Yeah. So in this video, I'm showing you the top of Casablanca volcano. We hiked on that volcano, and you can see that behind me, there's a lot of rocks. Those rocks have a different color and have a different texture. The rock, for example, over there is brown, and it has a black color. It has a little bit of white there. So we take those samples and we analyze them. What we want to know is the composition of that rock. We want to know the age of that rock, and by knowing the age of the rock, we know the age of the eruption. Okay, so what we see in there is lava. It's lava that crystallized over time. So it's basically lava that I'm going to show again here. Basically lava that came out of the volcano and then crystallized over time. So what we're seeing over here is just eruptive products that came out of this volcano. In this case, is Mochochoswenco. Now, many times we cannot hike to the volcanoes, and in that case, we use helicopter. I'm going to show you some videos from it. So many times it will not be possible to hike to the volcano, and in that case, we're going to use an helicopter and land, especially on these peaks that it's impossible basically to walk on. This is the Arica volcano. We can also see that there's some rocks in there that are covered by this tephra here, and it has different colors. In this part, it has a red color. So we basically want to know the age of those rocks and what is the composition of those rocks. Now, there. Now, when we plot all the earthquakes in the world in a globe, we can see that the earthquakes draw the tectonic plates. So, for example, this is the Nazca plate going underneath the South American plate, the Pacific plate here underneath North America. I made this rectangle here to indicate Madison, no earthquakes at all. And I made this rectangle here to show Chile. We have a lot of earthquakes. When I went there in December, I felt 4. We're very used to them. And when we plot the volcanoes by the same way, we can see basically the same. So we're drawing part of the tectonic plates. Madison, no volcanoes. Chile, a lot of volcanoes. And why is that happening? Is because of the tectonic, the theory of the tectonic plates. So basically, the motion of plates underneath are both making earthquakes happen and also volcanoes. So we have 3 volcanic settings in which the volcanoes are being formed. One is the spreading ridge volcanism. A good example would be Iceland, in which there are 2 tectonic plates that are being separated, and then the mantle melts, and the magma from the mantle that just melt goes to the surface. We also have hotspots in which the mantle melts and also that the magma comes to the surface. And a good example would be Hawaii, And we have the example that we're gonna talk more here, which is subduction zone, in which a tectonic plate goes underneath another one. There's water that enters the magma, facilitates the melting, and hence originate magma that can go through the surface and form volcanoes that are aligned perpendicular to the subduction. How are volcanoes being formed? There are two styles of eruption. There's one is called effusive and one that is called explosive. So the effusive eruption is the one that just generates lava. And you can see this, that red color that just was showing that GIF video is just lava that is increasing the size of the volcano, but to the width. So the extension of the volcano. There's another type of eruption, which is the explosive one. And those eruptions, what they do is they increase the height of the volcano. So now that ash, that column, the eruptive column will deposit on the top of the volcano and will increase the ash. So the volcanoes that we see in Chile, many of the volcanoes that we see in the Cascadian are in USA, are these stratovolcanoes that are called, or composite volcano, because they're formed by two different types of layers. One is called explosive and one that is called effusive. Now, in the past, it was thought that the magma chamber underneath this volcano would be like a circle, so a pool of magma that is underneath it. We have proved now this model here that is more called like a magma plumbing system, which is basically a system of like a network of different chambers that are being connected that are very small. And the eruptions occur when there's a disruption in temperature, the pressure, or the water content. And that's why the eruptions start to happen. Okay? Now, there's hypotheses that indicate that volcanoes can not only erupt by internal processes, like those changes in temperature, pressure, and water content that I mentioned, but also because of external processes. For example, landslides, earthquakes, and in this case, which would be glaciation. So the hypotheses indicate that the ice that is covering a volcano, by glaciations, a very big and thick ice, is making the magma to pool in the mid-crust, which reduce the eruptions, make the magma to just chill in there. And then when the ice retreats, the eruption occurs very rapidly because there's magma there that just want to come out. We see in this figure also, without glaciation, just volcanoes erupting. During glaciation, the crust bends like that, in that form, because of the stress that the ice is producing, and then makes the magma to pool there and the eruptions to completely inhibit, apparently. Now, when the ice retreats, there's a crustal rebound, which makes the magma to reinitiate in a very rapid way because there's a lot of magma that is being stored there in the mid-crust. So the way I see this, like a pressure cooker that is impeding the food to come out, and in this case, the magma. So imagine like the pressure cooker is the magma plumbing system. What is inside the pressure cooker, the food, is the magma, and the lid would be the ice. Okay, so we want to know what kind of food is there. So what is the kind of magma? What type of magma is it? What is the composition? And we want to know what is the size of the magma plumbing system, so the size of the pressure cooker. And we want to know also what is the size of the lid. So what is the size of the glacier that is covering? Something very important also is that when we open a pressure cooker, we first press a button, right? If we don't do it, something like this happens. So how do the lid stick out of the magma plumbing system? How the glacier retreats? Does it retreat very slowly or retreat super rapidly? We make the magma to erupt extremely explosively. So those are the questions that we want to know. Those are the questions that we have and want to answer. There's another hypothesis that indicates that there's a change in the composition of the magma plumbing system, and I don't want you to focus too much in this thing in the bottom, but here in this figure on the top. that indicates sorry, that the ice can make the magma to pool in there and makes the magma to change in composition. So when the ice retreats, the eruption occurs super rapidly in a more evolved magma. So how do we test this hypothesis? First, we want to know the time. We want to know the age of the eruption. We want to know the volcano at what time did it erupt, and want to know the age of the glaciation. When was this volcano covered by ice? And I put this figure because I really like this movie. This movie is called Shock and Redemption from 1994. This guy, Morgan Freeman, is the narrator. And he says at one point, geology is a study of pressure and time. And that's basically all it takes, pressure and time. And it's funny because that's the thing that we're studying. We're studying how the ice is putting pressure on the magma system and at what time that is happening. Now, we also want to know the type of the eruption. There are two types, as I said before. This type here is an eruption that is more explosive. It generates a lot of ash, a lot of fragment because of how explosive it is. And sometimes the material is so dense that doesn't travel through the atmosphere, but it goes down the flank in a pyroclastic flow, which is the most hazardous process that could happen in a volcano during an eruption. Another type of eruption is diffusive, as I said before, which is just magma coming out of the volcano. It's not that dangerous. We can be much closer. We can look at these eruptions usually, but still, obviously, we don't want to be that close either. And we want to know the size of the ice. So how big is the lid of the pressure cooker? And for that, there are already some models that indicate how could it happen, but those models had a bit of uncertainty. These red lines here indicates that the ice was in there, but the uncertainty of those models is super high. I'm sorry. Now, why are we studying Chile? Is it because the volcanoes are beautiful? Yes, but not only because of that. It's because the southern volcanic zone in Chile comprises more than 30 volcanoes. And we know that those volcanoes in the past were covered by at least 1 kilometer thick of what is called the Patagonian ice sheet. So there are 30 volcanoes that were covering, those volcanoes were covered by a lot of ice. So we can know by studying the past what is going to happen in the future, basically. Basically what a geologist does. And by doing that, and to do that, basically we collect samples. We collect a bunch of samples. In this case, this is a bomb that we call is a big, very piece of rock, of lava that crystallized in there, and it falls on the top of a volcano. This is a lava flow that crystallized, and I'm there with a colleague making some measurements. This is another lava here that has this texture. That means that it could be because the lava was stopped by contact with ice or with water. And we have also these lava flows that are super nice. They have pahoehoe texture based on the eruption that happened in Hawaii. Now, how do we do this? How do we know time and how do we know the composition? We basically apply dating methods to know the age. And to know the composition, we apply geochemistry. Okay? So we first collect the sample. We look at it in the microscope. And then we see the grains that are in there, and we analyze the composition of those grains in the microprobe, in this instrument. If we want to know the age, we put very tiny amounts of samples in these tiny holes, and we analyze the argon in this instrument. Now, I'm not going to talk very much about the instrument, about the argon method that we perform, but it's very challenging. It's challenging because of the composition of these samples, but I'm going to say that when I get an age, I get very happy. So by knowing the age of the eruptions, and by looking at this outcrop, we can infer some things. In this photo here, I'm showing a lava flow that has a specific age. And that lava flow has a texture that could indicate that it was contacted by ice. This lava flow here apparently has around 18,000 years. It's around 18,000 years old. It also has lava ice texture. It's been thickening by the ice, probably because that it was so big that it was being stopped by it. And we're inferring that the extension of the ice was at least at that elevation. Now, how do we know the size of the ice? For that, we're not doing that. And I put the photo of 3 persons in our department. This is Sean Marcotte, with the advisor Yasmin Orellana, Salazar, and Matias Romero. And Yasmin is Chilean and Mati is Argentinian. And they're studying the size of the ice by looking at this uncertainty. So they try to make all these red lines and orange lines like more green. So some results that I'm going to show you is that apparently the volcanoes do not stop erupting during glaciation at all. In fact, apparently they continue erupting without any problem. What is thus happening apparently is that there's a restriction in the magma plasma system, which makes the composition of the magma to change. Now, the ice is so thick that produces stress here, and that stress makes the magma to evolve into a different composition. And when that's retreated, the eruption occurs very rapidly. But apparently, ice doesn't make eruption to stop. And now, what I wanted to finish with this slide, I wanted to show a little bit about what I do here. I'm from San Bernardo, Chile, which is the southern part of the capital, Santiago. And why I studied geology is basically because I really like dinosaurs, I really like minerals, I really like volcanoes. And my father, when I was 5, he told me like, hey, you know, like this, there's this career that incorporates all the things that you like, and it's called geology. So that's why when I was 5 years old, I was already wanted to study geology. Also, my father, he was born in Bolina, which is a town very close to Kisapu volcano, which the 1932 Kisapu eruption was one of the largest eruptions in the 20th century in the world. So his father was always talking about the eruption, and hence my father was also talking about the eruption all the time. Now, something that I could say, and I would like to say this because we always think that undergrad is easy. I think it's super difficult. It's probably most difficult than grad school, at least in my opinion. My parents didn't go to the university and didn't do grad school, so I'm a first generation undergrad and grad student. It was difficult to enter undergrad because I even though I wanted geology since I was 5, it was very difficult the first years. Despite that, I just decided to continue going because I really liked it. So I'm this kind of person that thinks like, if you like that something, you just go for it. And just don't compare to anyone, just go for it, and at some point it will be fine. And I think my siblings did the same, because even though my parents didn't went to university ever, my siblings both have also master and PhDs. So there was something that my parents were building on us. That was like, you need to do the things you like. So yeah, I would like to acknowledge a lot of institutions. First, the NSF, which is financing, funding part of this project. The Agencia Nacional de Investigación y Desarrollo del Gobierno de Chile, which is funding my PhD. So I earned a scholarship there for this institution. They're funding my PhD. The Whiskar Lab, which is where I work. The CONAF, which is the forestry survey in Chile. And we have projects with them in which we are showing how the volcanoes erupt. We try to connect more into outreach by outreach to show people about the volcanoes, and also Fundación Willow Willow, which is also a private park that is around these volcanoes. So yeah, that would be my talk. I leave the website of the Whisker Lab and my Twitter. Please let me know if you have any questions.